In this clip, we're going to explain how do we measure the performance of the network, especially what we call grade of service or level of service. Okay, so for our purpose, we're going to consider cellular voice service. Okay, so the grade of service, which we can use this shorthand GoS, right, can be measured by the probability of call blocking. So when we say probability, it's range from 0%, that means it's never gonna happen, to 100%, that is it's gonna happen for sure, or between 0 and 1. So we're gonna measure the probability or the likelihood that when you make a call, the call will be blocked. If the call is blocked, then the customer will not be happy. And that's one way to measure the level of service provided by the network. So if you look at call blocking, that's going to happen when the number of call requests from the user is bigger than the number of channels available provided by the base station at some cell that the users are in, right? So when there are more calls, then the number of circuits or the number of channels at the base station, then the call has to be blocked and the request for connection will not be successful. Now, how do we analyze this probability? The grade of service in this context will depends mainly on these three factors. First, the number of available channels at the base stations. So the more the bigger the number of channels is, then the less likelihood that the call will be blocked. The number of channels will be denoted by variable C. The second factor is what we call arrival rate. So that is the number of call requests or call from the user that is try to connect to the base stations. We're going to use lambda to denote this variable. So lambda could be something like 100 call per hours, right? So it's the number of call per certain period, or 10 calls per minutes, okay, something like that. Okay, and the last factor is average holding time or service time. So whenever the user got connected, how long they stay on the network or stay on that circuit or on that channels. The longer they stay, the less likely that the people who are waiting or who try to make a call will get connected. This average holding time or service time, we're going to use capital H to denote this factor. And at the end, we'll analyze and get some grade of service. For example, in some service, they might say blocking probability. So P subscript B, this denote blocking probability. They might want blocking probability to be less than 2%. Okay? So certain network have some target blocking probability or grade of service that they want to satisfy, so that it's not going to be the number is not too big, so the user will be less likely that they're going to get blocked. So if blocking probability of grade of service is less than 2%, that means what it means is on average, right, average of 100 calls, at most 2 calls or less are blocked, right? So that's what it means by 2%, right? So 2 out of 100, less than 2 out of 100. Okay. Now, before we get to how do we compute or analyze or predict this call blocking probability, we have to find a way to measure how intensity uh, the traffic is. So traffic here is how busy or how big is the number of call requests to get connected to the base stations. Okay, so how intense is the traffic, right? This can be measured by these definitions, right? So the average usage time of the network divided by the total network. That's going to measure how uh, traffic intensity at that networks is going to be. So average usage time, this is in terms of time unit. Total time, that's also time unit. Okay, so at the end, if you divide this two variable, then you get some number without any unit. we're gonna call this variable A. So A will denote traffic intensity. The bigger the A is, that's gonna mean the busy the network is, or the busier the base station is. So the unit of A is Erlang, or short with ERL. Okay, so ERL or Erlang is the unit of traffic intensity. This can be measured by the average usage time divided by total time. Okay, so let's look at some example. So let's see, user use phone for voice call on average 6 minutes per hour. So how much is the traffic intensity in this case? So what is the A? So in this case, A is the average usage time is 6 minutes. So it's 6 minutes, say per hour. So that means we consider total time for 1 hour. 1 hour is 60 minutes. So in this case, it's 6 divided by 60, or 0.1, and the unit is Erlang. Okay. So this network or this channel or this circuit will be busy, or will have this traffic intensity of 0.1 Erlang. Okay, on average. Let's move on to example number 2. A voice circuit is occupied fully during 1 hour period. Okay, so fully, that means A will be used 60 minutes out of total time of 60 minutes. So that means this is equal to 1, or 1 Erlang. Okay, so this is the maximum traffic intensity for one channel. That means that the channels get used all the time, right? So if anyone try to connect to that channel, it will be rejected, or it will be blocked for sure. Okay. The last example is, what is the maximum traffic intensity for 30 voice channels? Okay, so we see that for one channels, the maximum traffic is 1 Erlang. So if you have 30 channels, then the maximum traffic intensity would be 30 Erlang. Okay. Okay. So the way we compute traffic intensity, well, it depends on how often the call arrive or try to connect to the network, and also on average holding time. So it turns out traffic intensity is equal to lambda multiplied with the h. So what is lambda? It's the call arrival rate. In terms of number of calls per minute, or per hour, or per some time unit. Okay. And then h, capital H, is the average holding time. This is in terms of minutes or hour. Okay. But when you put these two numbers together, the units for time has to be the same. Okay. And then at the end, you get an A, or traffic intensity. Example, if there's a call arrival rate of 1 call per minute. So that means on average, per minute, there's going to be 1 call try to connect to the network. The average holding time for each call is 2 minutes. What is traffic intensity? Okay. So A is equal to lambda multiplied with H. Lambda is 1 call per minute. H, right, is 2 minutes. Okay. And you see that minutes cancel with minutes. Okay. So A is equal to 2 Erlang. Okay. Okay. So with this in mind, we are able to move to how do we predict uh, blocking probability. So we have to assume certain model of the traffic. And in this class, we will use what we call Erlang B model. Okay, so what is Erlang B traffic model? Here's the assumption of this model. First, whenever call is blocked, that call will be clear or disappear from the network. So if you try to make a call, right, to a certain network, right, maybe it could be AIS, or it could be true. Once you make a call, but you got this signal of, no circuit available, or you cannot connect, then the call is blocked, once the call is blocked, you or the user will not make a call again, right? Will disappear. That means you don't make a call, you switch to another network, right? Right. So this is what it called block call is clear. Okay. And the arrival rate, right, or arrival process has this Poisson uh, distribution. So Poisson is the random process, right? If you want to know more about this, you can read the book, right? What is Poisson random process? Okay. And the holding time, right, for each call, this is random variable. From Erlang B model holding time, we have this exponential distribution, right? Or holding time is an exponential random variable. Okay, so this is with this assumptions, right? We can analyze blocking probability or probability of call blocking. So we use PB for blocking probability. So PB will range from 0 to 1. 0 means 0%, right? Never gonna be blocked, right? 100 on 1 means the call will be blocked for sure. So you want PB to be as low as possible, right? The lower PB is, the happy the customer is gonna be. Okay, and the formula is this. So A, remember, A is traffic intensity. In this case, A is offer traffic intensity. Offer means it's the traffic, total traffic that try to connect to the network. Okay, this is in terms of Erlang. Okay, and it depends on C, the number of channels or the number of circuits available at the base stations. Okay, so the formula is A raised to power C divided by C factorial divided by a to the power k, k factorial, and this is going to be the sum from k equal to 0 to k equal to c. Okay, so this means summations, right? Sum start from k equal to 0 and k go to k equal to 1, right? You just plug in k here, right? And then you keep going until k equal to c. That's going to be the last index, right? You put that in this formula and you add them together. Okay, so let's take a look at example. So certain network, right, has, for example, two channels, right, and traffic intensity is equal to 2. Okay, so that means only two channels, right? And that means there's a lot of traffic, right, compared with the two channels. So let's compute blocking probability. So if you use the formula, so A is 2 raised to power 2 divided by 2 factorial. Okay, so this is what you get. Divided by, okay. So first, this is when k equal to 0. So you get 2 to the power 0 divided by 0 factorial. And then you go to k equal to 1, right? So 2 raised to power 1 divided by 1 factorial. And you stop when k equal to 2, right? Or k equal to c. Okay, so denominator consists of 3 terms. And you do computation, it's 0.4. That means the chance of getting call block is 40%, right? So 40% is a big, big number, right? So it's closer to, every two calls, the call will be blocked, right? So that's almost, getting very close to 50 to 50, right? Yeah. So what if we increase, right, the number of channels from, right, 2 to 3? The level of traffic stay the same, okay? So according to the formula, so it's 2 to the power c, right? C is 3 divided by c factorial, right? So remember, this is the formula that we are using, okay? Divided by the sum, right? So since uh, the c, right? C is bigger, right? So the number of terms will be bigger, right? So k equal to 0, 1, 2, and then 3, there are 4 terms, yeah? So if you compute this, you get 0.116. Okay. Okay. And then you keep going, right? If what if the number of channels increases to 5, right? So you put in into the formula, you see that for the denominator, which consists of the sum, right, there's going to be more terms, right? And you see that uh, the probability of call blocking keep decreasing, right? Because we increase the number of channels, but the traffic intensity stay the same. Okay, C is equal to 7, and then A is still 2, right? So the blocking probability decreased to only 0.3%, right? Okay, so that means if you increase, if there's more resources, right, more channels, and traffic intensity stay the same, right? The likelihood, the likeliness that you're gonna get blocked will be small, right? Getting smaller and smaller. Okay, and you see that as the number of channels increases, if you use the formula, right, you see that the denominator will, the number of term will keep increasing, and this is gonna be difficult if you use your calculator, right? That means there are many terms that you have to calculate, right? Right. So C if equal to 10, 20, then it's more complicated. So it's useful to use the chart, right? This is what we call Erlang B chart. So what is this chart? See that the x-axis, this is traffic intensity. So this is A in terms of Erlang. So you look at this, this is A equal to 0 0.1, 1, 10, 100. So this is in log scale. Okay. And the y-axis, this is blocking probability of PB. So starting from 0.001, right, or 0.1%, right? 0.01 and 0.1, right? 0.1, that means 10%. This is 1%. This is 0.1%. Again, this is in log scale. So the x-axis in log scale, the y-axis also in log scale. Now you see different graph here, right? So what is this? It depends on the number of channels, right? C. So the first one is this when there's one channels, right? When there's two channels, you use this graph. 3, you use this, right? And then 5, right? Then you go to 10, you use this. 20, yeah, 30, right? So there are many values of C for you to look at, right? So how do we use this? Let's look at example. Okay. So let's see, there are certain network that you want blocking probability to be less than 0.01, right? No bigger than 0.01. And the network has traffic intensity coming for 10 Erlang. So what should be the number of channels that should be installed for this network, for this base station? Okay, so if you use the formula, right? So blocking probability, you plug in 0.01. So A is 10A to the power C divided by C factorial. Okay, and then there are summations, right? 10 to the power K factorial K from 0 to C. The question is what should be the C? Okay, now how do you solve this, right? Right, because the C is also the number of terms, right? One thing you can do is, it's easy to just use this Erlang B chart. Okay, so let's see how can you use that. So first, A is equal to 10. Okay, so A is equal to 10. That's gonna be this vertical line, right? Okay, okay, that's A equal to 10. And we want blocking probability of 0.01. Okay, 0.01 is right here. So if you look for the horizontal line is this one, yeah, right? Okay, so that's the target, right? Okay, so let's see what can you do, right? So if you use this, right, then if it's 10, right, then then it's gonna be right here, right? It's gonna cut over here. So that means the blocking probability is gonna be a little bit higher than 0.01, right? So maybe you use one more, you know, increase the number of channels. So instead of 16, is it 16 or 17, right? You use 18, right? So 18 is right here. So sorry, this is not, this one is 17, yeah? What if you use 18, yeah? So 18 is right here, yeah? So this is where A is equal to 10, right? So A is equal to 10, right? So you see that blocking probability is less than 0.01, right? So 18 is okay, 17 is not okay, right? So the answer here, C, should be 17. Yeah? Okay, so the chart is very, very useful and very handy.